Excuse me. Okay, so my YouTube is on. So let me get to the PowerPoint, the full screen. Okay, so if I remember correctly, the last time we were here, we stopped at, I think this is where we stopped at, where we discussed the periodic table and the different types of elements and classifications and so on. All right, so the next thing we're going to discuss is compounds, and in particular, we'll be talking about the nomenclature, how we name compounds based on their formulas, and vice versa. If you're given a name, how you can determine their formulas. So firstly, and again, this is something that you would have covered in your introductory or high school chemistry. So again, I'm going to go through this rather quickly. So here we're talking about molecules. And of course, you know that a molecule is a group of two or more atoms that are held together by covalent bonds. And later on, we're going to discuss the nature of covalent bonds, which are basically bonds that holds atoms together as a result of atoms sharing electrons, all right? But that's for a later discussion. So let's talk about the chemical formula, which of course is a symbolic representation which indicates the composition of a particular compound. So here's an example, B2O3, right? That's an example of a chemical formula. It tells you what elements are present, in this case, which would be boron and oxygen, and it tells you the number of atoms of each element present per unit. So you have 2 boron atoms for every 3 oxygen atoms, all right? So that's a chemical formula, or that's an example of a chemical formula. So what we're going to talk about are molecular compounds in this section, and we're going to talk about how we name them. So here are some examples of molecules. You have chlorine, which exists as a diatomic molecule. In fact, there are 7 elements that exist as diatomic molecules in nature. And you need to know them. In fact, let me write them down here. Hold on. Okay. Oh, this thing is not plugged in. I'm sorry. Let me plug this in. Okay, let's see here. All right. Okay, so there are 7 elements that exist as diatomic molecules. You have oxygen, nitrogen, fluorine, hydrogen. Let me put hydrogen here as the first one. Oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. These are the 7 elements that exist in nature as diatomic molecules. So if you're given a question and the question mentions any of these elements, you should immediately understand that in nature, we're talking about them existing as diatomic. So chlorine is one example here. And then you have some elements that exist as polyatomic. Sulfur is one of them. And then there's only one other. Sulfur exists as 8 sulfur atoms per molecule. And phosphorus exists as 4 phosphorus atoms per molecule. All right. Then we have others, which are compounds made up of different elements, such as the one that you see here. This represents a formula for acetic acid. It's a ball and stick model representation where the black spheres here and here represents the carbon atoms. And the white spheres represents hydrogen atoms. So these are all hydrogens. And the red spheres represent oxygen atoms. So these are oxygen atoms, right? So this is something, for those of you who plan to do organic chemistry, you'll be meeting this sort of representation a whole lot, the ball and stick model. It's very useful because not only shows you how the atoms are connected to each other, but it also gives you a picture of the shape of the molecule, which can have a profound influence on the properties that compounds will undergo, all right? Basically what you'll find is that in a lot of cases, the actual 3-dimensional shape will influence the reactions that the compounds will undergo, all right? So that's a ball and stick model here for acetic acid. And then this is what we call a space filling model representation of the same compound. Now this is useful in terms of looking at the relative sizes of the atoms. So not only does it tell you what atoms are connected to which atom, And not only does it give you the shape, but it gives you a picture of the relative sizes of the different atoms, which can become important, especially if you go into, high-level research, when you're looking at things like drug interactions and so on. A lot of times you have to take into account the amount of space that a particular atom will occupy, or for that matter, the molecule, and not just the shape, all right? So these are just different representations of molecular compounds. As I said before, you'll meet them in the future. Okay, so when it comes to formulas for molecular compounds, there are two types. You have what is known as the empirical formula, and you have the molecular formula. So the empirical formula, by definition, gives you the simplest whole number ratio of the atoms of the elements present in a compound. So that's the empirical formula. While the molecular formula gives you the actual number of atoms of each element present per molecule. So to use an example, the molecular formula of glucose is given right here. It is C6H12O6, all right? But the empirical formula of glucose is CH2O, all right? And basically you can get from the molecular formula to the empirical formula by dividing, in this case, right through all the numbers here, the subscripts, by 6, all right? And that is basically how you get from the molecular formula to the empirical formula, right? Very easy. Now, what is more challenging is getting from the empirical formula to the molecular formula. And the reason why it's more challenging is that you're going to need more information in order to get to the molecular formula from the empirical formula. You're going to need to know, for example, what the molecular mass is, or the molar mass, all right? And we're going to see this example. You can do some calculations where you multiply this by a number known as the integral factor, and that will convert your empirical formula to the molecular formula, all right? Okay, structural formulas. Again, this is something for those of you who have to do organic chemistry, you're going to meet, all right? So for example, what it tells you basically is how the atoms are connected. When you're given a structural formula, it's not giving you information about the shape of the molecule. It's not giving you any information about the three-dimensional arrangement of the atoms. So basically, and it's not giving you any information about the space-filling properties of the atoms. It's just basically showing you how the atoms are connected to each other. And in some cases, that's all the information you're going to need, all right? So for example, in the case of ammonia here, it shows you that the structure of ammonia is made up of nitrogen connected simultaneously to 3 hydrogen atoms. In this case, the carbon of methane will be connected simultaneously to 4 hydrogen atoms. And in the case of acetic acid, which we met earlier, this is the resulting structure. It shows you how the atoms are connected to each other, all right? So these are the structural formulas, and they're relatively simple to understand and to use, all right? Okay, so let's talk about binary molecular compounds. So binary molecular compounds, we already know what molecular compounds are. These are compounds which consist of molecules, which are a collection of atoms, non-metallic atoms held together by covalent bonds. Now, the term binary basically means that these molecular compounds consist of only 2 elements, all right? And here are 3 examples right here. You have carbon monoxide, you have nitrogen monoxide, and you have hydrogen fluoride. And I can mention a couple of others. For example, sulfur dioxide, carbon tetrafluoride, sulfur dichloride. These are all examples of binary molecular compounds, because in each case, you have basically 2 atoms or 2 types of atoms making up that particular molecule of that compound, all right? Now, in terms of the convention that is oftentimes used in chemistry, when it comes to writing down the molecular formula for these compounds, we start off with the more metallic element first, followed by the less metallic element. Now, these elements are not metallic, but basically it's based on their electronegativity values. The least electronegative element is placed first in terms of the formula or the symbol, followed by the more electronegative element, all right? So another way of looking at it, as stated here, that the one that is more metallic is the element that is more towards the left of the periodic table and down or lower in the group, all right? So that's another way of basically determining which element will be represented first in the molecular formulas, all right? Or you could memorize this, which I don't expect you to do. This is a bit hard to memorize, so I won't expect you to memorize this, but you can use this as a guide in terms of, again, predicting which element will be indicated first in the formula, all right? But You don't need to memorize that. Basically, it comes down to electronegativity values. The one with the lower electronegativity value of the two elements that make up the binary molecular compound, the one with the lower electronegativity value is the one that is placed first in the formula, followed by the other element. Okay, so let's look at how we determine, how we write down the formulas. And it's very simple. Again, this is something you would have met before. We write down the formulas. Remember, the least or the less electronegative element will be indicated first, but we also include the number of atoms of each element as a subscript, with the exception of if there's only one atom, then it's not necessary for you to place one as a subscript. Nothing wrong with you placing one, but it's not necessary according to the rules, all right? Excuse me. So these are a couple of examples shown here: H2O, CO2, N2O, HF, and B2O3. And just by giving you the formula, it gives you some information about the composition of the compound. So for example, in the case of N2O, this tells you that there are 2 atoms of nitrogen and 1 atom of oxygen present in this compound, all right? So then we get to a question of how do we name these compounds? Well, what you're going to find is that when it comes to binary molecular compounds, not only do you indicate the number of each, the type of each element that is present, but you also have to indicate the number of atoms of each element that is present per molecule. And we're going to see how that is reflected in the names of these compounds. So in order to illustrate how we name these compounds, I'm going to use these 2 examples, CO and CO2, all right? How do we name these compounds? Let me just say that the system of naming these compounds, before I get into this example, is developed or has been developed by an organization known as IUPAC, International Union of Pure and Applied Chemists, all right? And there's a division of this organization that meets, if I remember correctly, every 2 years. And their sole purpose is to come up with rules for naming compounds, because as you can imagine, there are new compounds that are made up or, created every year. And, sometimes the new compounds provide a challenge in terms of naming it based on the existing rules. And therefore they have to meet ever so often in order to come up with new rules to accommodate these new compounds, all right? So what we're about to discuss are rules that were developed by the division in IUPAC, International Union of Pure and Applied Chemists. So as I said before, we're going to use this example, CO and CO2, molecules represented by these 2 formulas, all right? So as stated here, the compound name for these 2 compounds will be consisting of 2 words, one for each element in the compound, right? Now, the first element that is indicated in the formula is carbon. So therefore, the first name of each of these compounds will start off with carbon. Now, the second element, the name of that element, according to IUPAC, has to be altered. So the element here is indicated as oxygen. But in the name of this compound, we have to basically modify that name by replacing the ending of the name with IDE. So in the case of oxygen, we replace the YGEN by IDE. So oxygen becomes oxide, all right? So carbon remains the same, right? We don't make any modification to that name, but for the second element, we modify it by replacing the ending of that name with the suffix IDE, all right? Now, this still begs the question, how can we tell these 2 compounds different by their name, right? So we cannot have both of them having the same name, carbon dioxide, because they both are different compounds. So we have to find some way of indicating the composition of the different elements in each compound in their name. And basically, that brings us to what we call the prefixes that are used when it comes to naming binary compounds, right? According to IUPAC, you have to use the appropriate prefixes when it comes to naming these compounds, all right? And these are the prefixes that we'll be using. There are more, but for all purposes, we'll stop at a situation where the number of atoms in a particular molecule is 10. So as you can see here, we have for one, the prefix is mono, for 2, the prefix is di, For 3, the prefix is tri, and so on, tetra, penta, all the way to deca, all right? So how do we apply the prefixes to naming these compounds? Well, in the case of the first one, I'm sorry. In the case of the first one, in fact, let me bring up my my writing tablet here. So since I don't have any space, and let me clear this here. Okay, so in the case of CO, the name of this compound will be carbon monoxide. All right, monoxide, because there's only one carbon atom that is present in the molecule of this compound. And then in the case of CO2, the name of this compound is carbon dioxide. Di, of course, because there is a 2 here, all right? So that's basically how we can distinguish between these two compounds in terms of the name. The name of the one with only 1 oxygen will be carbon monoxide. The name of the one with 2 oxygen will become carbon dioxide. Now, let me just say something here. You might be wondering, why is it that we don't use a prefix for the carbon here? So for example, in this case here, this carbon has 1 atom, this carbon has 1 atom. So why don't we use mono here and mono here? All right. Well, according to the good folks at IUPAC, they said, or they decided that if the first atom has only 1 atom, if the first element in the formula has only 1 atom represented, right? Then according to IUPAC, there's no need for you to use the mono prefix, all right? So in the case of CO, it's simply carbon monoxide and not monocarbon monoxide. In the case of CO2, it's simply carbon dioxide and not monocarbon dioxide, all right? However, if you had a compound like this, in fact, let me go back to the PowerPoint. I think I have the example there. Okay, here's one example here. If you have a compound like this, N2O3, right? In this case, you have to use a prefix for indicating the number of nitrogen atoms, all right? So therefore, in this particular case, the name of this compound is dinitrogen, whoops, sorry about that, dinitrogen trioxide. And a similar thing happened here. The name of this compound here is dinitrogen tetroxide. And in this case here, the name of this compound is dinitrogen pentoxide, all right? So if you have more than 1 atom represented for the first element in the formula, then you must use a prefix for indicating the number of those atoms. You'll notice here, for example, in the case of SF6, there's only 1 atom of sulfur, which is the first element indicated here. So we do not say monosulfur hexafluoride, we simply say sulfur hexafluoride. Down here, let me jump to this one right here, P408, the name of this compound is tetraphorus octoxide, all right? So that's basically how we name these binary molecular compounds. Now there's one other type of binary molecular compound that I want to talk about, which is not, unfortunately, in my PowerPoint slide, but let me deal with that example here. We're talking about elements, hydrogen combined with a nonmetal. So for example, HF, right? According to the rules, no prefixes must be used in the case of, let me write it here, no prefixes for any compound, any molecular, any binary molecular compound which has hydrogen bonded to a nonmetal. So this is a nonmetal, all right? So according to the rules, there are no prefixes that you use for any of the elements involved. So let me just give you a couple of examples. So this compound is known as hydrogen fluoride. All right, no prefix is used, right? Let's look at this one, H2S. This is known as hydrogen sulfide. All right. Let me do another one, HCl. This is known as hydrogen chloride. All right. So in all these cases where you have hydrogen bonded to a nonmetal, then basically no prefixes are used for any of the 2 elements involved, right? It's simply hydrogen, whatever, hydrogen fluoride, hydrogen sulfide, hydrogen chloride. Here's another one, H2SE. This is known as hydrogen selenide. All right. So that's how we deal with those compounds in terms of naming them. Okay. Any questions so far? Any questions? Any questions? Please feel free to ask any questions at any time, so that you can understand clearly what we're discussing. Okay, so we have talked about molecular compounds. Let's talk about ionic compounds, which of course are formed from ions. So I guess we have to have some discussion as to what we mean by the term ions. Ions are basically atoms that gain or lose electrons. And you can have two types of ions. You have those that are positive, which are known as cations. And you have those that are negative, that are known as anions, right? So basically, cations are formed as a result of an atom losing electrons. And anions are formed as a result of atoms gaining electrons, right? So here we have two examples where sodium will lose 1 electron to form a sodium ion, and chlorine will gain an electron to form a chloride ion. Later on, we're going to learn about basically how can you predict how many electrons will be lost or gained when an atom becomes an ion. So that's for a future discussion. So when we're talking about monatomic ions, which are ions formed from just one atom, here are some ways of predicting the type of charges or the number of electrons that will be lost. The group A metals, right? So we're talking about the metals which belongs to the representative elements. They usually lose a number of electrons equal to their group number, all right? While nonmetals usually gain an electron and have a charge equal to their group number -8, all right? So for example, before I move on to transition elements, so for example, sodium is in group 1A, so sodium will lose 1 electron to form the sodium ion. Calcium is in group 2A, so calcium will tend to lose 2 electrons to form the calcium 2+ ion. And let me see if I can squeeze it in over here. Aluminum is in group 3A, so it will lose 3 electrons to form the aluminum 3+ ion, all right? As far as nonmetals are concerned, as stated here, the nonmetals will gain electron and have a charge equal to their group number -8. So basically, if we were to use sulfur, which belongs to group 6, it will tend to gain 2 electrons to form the S2- ion, which would mean that, which would be the charge resulting as a result of the 2 electrons being added to the neutral atom. And as stated here, the charge will be equal to the group number -8. The group number of sulfur is 6, -8 gives you -2. So that's basically how sulfur ends up with the charge, or the sulfide ions ends up with a charge of -2. Okay, now let's talk about the group B metals, meaning the transition metals. Turns out that you cannot use the periodic table to determine the charge on the group B metals. So it's basically impossible for you to predict the type of charge just by looking at the position of the elements within that group, all right? So I would not expect you to know the charges, and especially since I've provided the tables in Canvas, which gives you a list of, in fact, there are 3 pages that gives you a list of ions with their charges. So you can basically refer to those tables. You don't need to memorize the charges for these particular elements, all right? Now, sticking to group B metals, you will notice that there are certain elements, in fact, most of them, where they're able to form multiple charges, all right? And we have to make a distinction between those particular ions of the same element with different charges. And the way IUPAC recognize them in terms of their nomenclature is that we use Roman numerals in parentheses added after the element name. So for example, let me go back to my writing tablet here. Let me clear this again. Okay, so for example, there are 2 ions that can be formed with from copper. You have what is known as the copper 2+ ion and the Cu+ ion, right? So these are their symbols, right? So the name of this ion, according to IUPAC, is copper 2 in Roman numerals, in parentheses, right? And the name of this ion here is copper 1. Again, in Roman numerals in parentheses, all right? So for example, when copper 2 plus combined with chloride, it forms CuCl2, right? When copper 1 combines with chloride, it forms CuCl. These are two different compounds. The name of this one is copper 2 chloride. And the name of this one is copper 1 chloride, all right? So according to IUPAC, if you have ions or elements that can form different types of ions of different charges, then you need to indicate the name of the charge or indicate the type of charge using Roman numerals in parentheses, all right? And there are several examples of these types of ions in the transition region of the periodic table. Okay, so these are just a few examples of the monatomic ions. We have the representative, the ones belonging to the representative part of the periodic table, the A-type elements, group 1A, 2A, 3A, 4A, all the way to 7A. Well, yes, to 7A. And then we have those in this region right here. And you'll notice that there are several of them that can display more than one type of charge. For example, titanium can display a +4 +2. Manganese can exist as +4 +2. Cobalt can exist as +2 +3, and so on and so forth, right? And you need to indicate in the formulas where these type of ions exist, you need to indicate in the formulas the type of charges carried by these ions, all right? Okay, so these are, of course, a very abbreviated table of the common monatomic ions. As I said before, we have more comprehensive lists in the tables that are provided in Canvas. Okay, so how do we name ionic compounds? I kind of touched on it before, but we're going to get into it again here. First thing you need to recognize is that when you're trying to determine the formula for an ionic compound, the net charge of the entire compound must be 0, all right? So in other words, the total number of plus charges must cancel out the total number of minus charges. So for example, in the case of sodium chloride, the sodium ion contains a +1 charge, the chloride ion has a -1 charge, so therefore there's a 1-to-1 ratio between these two, such that the charges cancel out. +1 - 1 is equal to 0, all right? And then when it comes to naming these compounds, we name the cation first, and then we follow with the anion name. So in the case of Na combining with Cl, the final name of that compound will be sodium chloride. So that's basically how we name these compounds, all right? Then we get to a situation where we can have what we know as polyatomic ions. And these are different from monatomic ions in that, in the case of polyatomic ions, the ion consists of a group of atoms held together by covalent bonds, and that group as a unit carries a charge. So there are some examples that are listed here. Such as CO3 2-, that's known as a carbonate ion. This one here, Cr2O7 2-, that's known as a dichromate ion. And we have PO4 3-, that's the phosphate ion. And we have S2O3 2- down here, that's known as a thiosulfate ion. So these are all examples of polyatomic ions. And you have to be careful when you're writing down the formulas containing these ions. In fact, we're going to look at a couple of examples right here. So let me get rid of this. Okay, so let's say you're given barium phosphate. You're given a name and you're asked to write down the formula. So the first thing you would do is go to the table that I provided for you in Canvas, and you look up the formula for the barium ion. And when you look it up, you're going to see that the formula is Ba2+, right? And then you look up the formula for the phosphate ion, and when you look it up, you see that it's PO4 3-. Now, looking at these, you'll notice that the number of plus charges is not equal to the number of minus charges, and therefore, we have to do something here, because remember I said that the charges need to be canceled out. So the question now becomes, how do we get these charges equal to each other? And basically what we have to do in this case is that we multiply this one by 3 and multiply this by 2, right? Because by multiplying this by 3, you're going to end up with a total of plus 6 charges, and multiply this by 2, you're going to end up with a total of minus 6 charges. So therefore, the formula now becomes BA3 parentheses, and please note, there's an open parentheses because we have more than one atom represented here in this polyatomic ion, PO4, close parentheses, and then this 2 here now becomes the subscript. So this would be the formula for barium phosphate. All right. So that's basically how we do that. Any questions about this example? Any questions? Any questions? Okay, here's another example. Suppose you're given okay, I'm going to do the opposite in this case. Suppose you're given this formula. SN3, no, I'm sorry, SN, SO4, 2. Okay, so how would you determine the formula for this compound? Anybody? Anybody? Let's start with Mr. Tyner. Any ideas? Mr. Tyner, Dalton?
I'm not quite sure. You want to
What would be your first step? Let's start off with the first step.
splitting up your 2 molecules?
Well, the two, well, well, not molecules, but
Or not molecules, but atoms?
the cation, the ions, okay, yeah. So when you split it up, you're going to end up with tin and the sulfate, right?
Yes.
So what do you think you would do next? Anybody else? Jacob? And and by the way, please note, let me just do this right here. There are 2 of these because of the 2 here, right? So what would be the next step? Jacob? Or Keisha? Cameron? Come on, you guys should be able to do this because this is something that you guys would have done from your introductory chemistry course. Natalie, any suggestions? Okay, let me try to help you guys along. What would be the charge that is carried by the sulfate ion? And you can look up the table in Canvas if you feel you must.
Isn't it -2?
Okay, -2, very good. So you're going to have a -2 here or 2 minus. It doesn't matter how you write it. You can write as -2 or 2 minus. Okay, very good. Okay, so what would be the charge carried by the tin? Anybody?
Is it +2?
Okay, so you're saying +2. Why do you say +2?
I
I want
just
to hear
think
your rationale. Why do you say +2? Why +2?
that's just what I saw.
Okay, well, let me give you a little hint here. Remember what I said, and let me write it down here. The total charge for an ionic compound must be equal to 0, right? So if this is +2 for the 10, and this is -4, because 2 times -2 gives you -4, then the total charge here would not be 0. It would be -2, right?
Yeah, but since it's -2, it would have to be +2 to zero out.
No, because you have a 2 here. Remember, the 2 here multiplies a -2 here. So the total charge carried by 2 sulfate ions would be -4. And +2 will not cancel out -4.
Okay, so
So
it's +4 then.
exactly. So therefore, the charge for the tin would be +4. All right? So now that we know that this is +4, what's the name of this ion? The SN4+ ion. What's the name of it? Anybody? What's the name of this ion?
Wait, what do you mean the name? Isn't it just thin?
No.
Are you talking about the binary?
Right. No, according to the rules that we discussed in terms of naming ionic compounds, you have to name the cation first, then you name the anion, right? This is a cation, right?
Yes.
4 + 4. So what's the name, the actual name? It's tin something. Tin what? Let me give you a hint here. Let me go back to the PowerPoint. Nope, not that. Well, 1 minute. Oh, it's stuck. Ah, oh. Remember what I said here. Group B metals capable of multiple charges have the corresponding Roman numeral in parentheses added after the element name. So what we're talking about here is that if you have an element that can display more than one charge, then you indicate the charge by the Roman numeral after the element name. All right?
So be 10 IV.
Exactly. 10-4 or 10 IV, which is 4 in Roman numerals, right? So that would be the name of this cation here. The name of this cation here is a sulfate cation. All right? So therefore, the total, when you put these together, when you put this together with this, the name becomes 10-4 sulfate. So that's basically how you determine the name of the compound if we're starting off with the formula for the compound. You have to determine the charges, and you have to determine, for those elements that can display more than one charge, you have to indicate what charge that is. So that's basically how you do that. There's one thing I should mention. If the element displays only one charge, then according to IUPAC, you do not use Roman numerals. So for example, in the case of sodium chloride, let me just squeeze it down here. In the case of NaCl, the name is simply sodium chloride. All right? And we don't use any Roman numerals for the sodium because there's only one type of sodium ion, and that is the sodium chloride ion. You don't have any sodium 2 or sodium 3 or anything like that. All right? Okay, any questions about this? Any questions? Any questions? Okay,
No.
all right. Now, the next type of ionic compounds we're going to talk about here, I don't think you'd have met this before. So this would be new to most of you, if not all of you. And these are compounds known as hydrates, all right? What are hydrates? A hydrate is basically an ionic compound in which the formula unit includes a fixed number of water molecules associated with the cation and an ion, all right? So for example, we have two examples right here, BaCl2, and there's a dot here, and then 2H2O, right? So basically for every formula unit of barium chloride that is present in this compound, you have 2 water molecules associated with it, all right? And here's another example, CuSO4, and then you have a dot, and then 5H2O, right? So what this is saying is that for every formula unit of copper 2 sulfate that is present, you have 5 water molecules associated with it, all right? So these are examples of what we call hydrates, because in the ionic structure of these compounds, you have incorporated water molecules, a fixed ratio or a fixed number of water molecules per formula unit, all right? Now, a couple of things I want to mention about hydrates, and that is, firstly, that it's very easy to convert the hydrate to what we call the anhydrous form. So I'm going to use the barium chloride example to illustrate this. So let me do this here. BaCl2 dot H2O. If you heat this compound to 100 degrees Celsius, then what will happen is that you will drive off the water and you're going to end up with the anhydrous form of barium chloride. This form is called the hydrated form. All right? So it's very easy to go from the hydrated to anhydrous by simply heating the solid, and you're going to end up with the anhydrous form and the water driven off, all right? And that's true for every hydrate. All you have to do is heat it to convert it from the anhydrous to hydrated. And the reverse is also easy to accomplish. All you have to do to go from the anhydrous to hydrated is add water, right? So this process is easily reversible. To go in one direction, you heat it. To go in the other direction, you add water, all right? Very easy to go from one to the other and back, all right? Another thing I want to mention is that in terms of the appearance, what you'll find is that in some cases, not in all cases, in some cases, you might find that there's a change in color, all right? And that is what is happening in the case of copper 2 sulfate with the 5 water molecules. So let me squeeze that down here. So if you take CuSO4, 5H2O, and you heat it, you're going to get the anhydrous form, which is CuSO4. And of course, the 5 water molecules will be driven off. Now, the color of this form here is blue. The color of this form here is white. All right. So if you heat the hydrated form of copper 2 sulfate, you're going to get the white solid, but you can also reverse it, right? By adding water to it, and you get the blue hydrated form. And that is what is being shown in this picture right here. The white stuff is the the anhydrous form of copper 2 sulfate. And this person is adding some water droplets to the anhydrous form, and you notice that it becomes blue, all right? So that's one thing you'll notice. Now, there are other cases, such as in this case here, where there's no color change, because in the case of barium chloride hydrated form, it's white on this side, and it's also the same color on this side. But there will still be a difference in terms of the appearance, because the hydrated form here has a sort of crystalline appearance, while the anhydrous form is more powdery in appearance. All right. So even where there's no color change, there's still a difference in terms of the appearance between the anhydrous and the hydrated form. All right. Okay. Now, in terms of naming these compounds, the rules are very similar to what we saw earlier when it comes to naming ionic compounds, but you have to take into account, the number of water molecules. So let me use the barium chloride example, BaCl2, 2H2O, all right? So the name of this compound is barium chloride, and to indicate the number of water molecules, we use the prefix di and then hydrate. All right, so that's how we name this compound, barium chloride dihydrate. Barium chloride, that's easy to understand based on this part here, but the dihydrate comes from the fact that you have 2 water molecules present per formula unit of barium chloride. Okay, so what do you think the name of this compound is? Anybody? Anybody? What's the name of this compound?
The copper sulfate?
Well, the name of the entire compound. Tell me and I'll write it down here.
Copper 2 sulfate?
Copper
2?
2 sulfate. So far, so good.
And is that like times water?
Well, it's a dot. It's not times. It doesn't represent times. It's just a dot. So how would you indicate this part in the name?
Would it be pentahydrate?
Pentahydrate, correct. Very good, all right? So that's basically how you name hydrates, right? You name the first part, just as you would name any ionic compound, and then the water part, you indicate the number of water molecules by using the appropriate prefix, and then hydrate after that, all right? Okay, any questions about this? Any questions? Any questions?
No.
Okay, so moving along. All right, tell you what, let me take a break here. I need to take a break. I'll be right back in the next couple of minutes, all right? Okay. Okay, I am back. All right, so let's talk about a group of compounds known as acids, right? Very important group of compounds in chemistry. What I'm listing here is basically some properties that acids display. The first one that is mentioned here is that they have a sour taste, right? Now, that does not mean that you can just go into a lab and start tasting substances to find out if they are acids, all right? This is just a statement of a fact of the property, this particular property of acids. And in fact, we actually consume acids in various fruits and other substances, such as aspirin is a form of acid. Vinegar is also an aqueous solution of an acid. And citrus fruits, such as oranges, lemons, and so on, they contain acid. So these are all substances which contains acid, which has, you know, a sharp sour taste associated with them. Acids also turn a substance known as litmus red, right? Litmus is basically a dye. So basically the litmus will take on a color depending on what they're exposed to. So if you expose the litmus to anything acidic, then it will become red. If you expose the litmus to anything basic, which we're going to talk about later on, it will become blue, all right? Another property displayed by acids is that acids react with reactive metals, not all metals, but most reactive metals to form hydrogen gas. And finally, acids will neutralize a base. We're going to talk about this reaction shortly. So these are just some basic properties of acids. And then we have what are known as bases, which are considered to be the chemical opposites of acids. They tend to have a bitter taste. Again, I would not recommend that you go about tasting substances in the lab to figure out if it's basic. And as I stated earlier, bases turn red litmus blue. And one important property that they display, which again, I won't recommend that you try this out in the lab, is that they tend to feel slippery on the skin. And the reason why that is so is because bases will react with oils on your skin to form soap, right? So that slippery feeling that you would feel when you're exposed to a base is actually soap that is formed as a result of the reaction with the bases or the base with oils on your skin. And the final property listed here is that bases will neutralize an acid. Okay, so that we have covered some properties, let's talk about some concepts and definitions according to this guy, Arrhenius, right? So Arrhenius came up with his particular definition of acids. And according to him, acids are compounds that when added to water, form a solution of hydrogen ions and an anion, all right? While bases are substances when added to water form solutions of hydroxide ions and cations. And the reaction between acids and bases to form a salt and water is said to be, or is called a neutralization reaction. All right, so that is basically all of this that I've just described here are concepts that were developed by Arrhenius. Okay, so as I said before, the reaction between an acid and a base forms a compound that is known as a salt and water. And the formula for the salt is based on the formula for the acid and the base that forms it. So in this simple example, we'll be reacting an acid, hydrochloric acid, with sodium hydroxide, all right? So the water is formed, as I said before, and it is formed as a result of the combination of the hydroxide from the sodium and the hydrogen from the acid, all right? So that means that whatever is left will combine to form the salt, which would be the sodium coming together with the chloride, all right? So basically, this is what happens. The sodium comes together with the chloride to form the salt, and the hydroxide combines with the hydrogen to form the water, all right? So as you can see here, the salt is the combination of a cation with an anion. The cation comes from the base, the anion comes from the acid, all right? So that's basically what happens in every neutralization reaction. Okay, so before I move on to naming acids, let me go back to my tablet here and just give a couple of examples of acid-base reactions. So if you're given, let's say, calcium hydroxide with reacting with, let's say, hydrogen bromide, all right, then you're going to end up with calcium coming together. The calcium here will come together with the bromide to form calcium bromide, and the hydrogen here will come together with the hydroxide to form H2O, right? Now to balance this, we have to put a 2 here and put a 2 here. And that would be the balanced equation for this neutralization reaction. So this is the base, this is the acid, and this is the salt, right? And of course, this is water, all right? So that's what happens in every acid-base reaction. Let me just do one more example and then we'll move on. So let's say you're given barium hydroxide and it's reacting with phosphoric acid. Again, same principle applies. The barium will come together with the phosphate. Now, when the barium comes together with the phosphate, the formula becomes Ba3, PO4, and then 2 outside the parentheses. And the hydroxide will come together with the hydrogen to form H2O, all right? And then we have to balance this equation. And to balance this, we're gonna need a 3 here, we're gonna need a 2 here, and we're gonna need a 3 here, I think. Oh, no, I'm sorry. Actually, you're gonna need a 6 here because you're gonna have 6 hydrogen atoms combining with 6 hydrogen atoms on this side to give you 12. So this should be 6 here. So that's basically how we balance a neutralization reaction. So let me just say, well, let me do this first. This would be your base, this would be your acid, and this would be your salt, all right? Now let me just say that the reason why it's called a neutralization reaction is because presumably what will happen when these two react is that they will cancel out each other's properties, right? So when a base reacts with an acid, supposedly the salt will not be either basic or acidic, it should be neutral. But let me just say that that is not going to be the case in all cases. And I won't go into that discussion because that would be saved for general chemistry 2. What you're going to learn in general chemistry 2 is that the salt that is formed from an acid-base reaction can be acidic, basic, or neutral, all right? And to determine whether or not it's going to be acidic, basic, or neutral is based on the actual strength of the acid and base that is involved in the reaction. And that's as far as I'm going to say about that, because that will be covered in more detail in general chemistry 2. Okay, so let me get out of this here. Let me go back to the PowerPoint. And let's talk about the names for acids. All right, now, when it comes to naming acids, I'm going to start off with the binary acids. So for binary acids, we're talking about acids which contain hydrogen and one other element. All right, so we're talking about HCl, H2S, and some others, all right? Now, when it comes to naming these compounds, you have to be careful. In fact, let me go back to my writing pad here again. So when it comes to binary acids, you have to pay attention to the state symbol, HCl, all right? Now, if HCl is in a gaseous form or gaseous state, this is called, let me write the name down here. This is called hydrogen chloride, all right? Now, if you add HCl to water, it becomes HCl aqueous, right? The name of this is different from the name that we have here. This is going to be called hydrochloric acid, all right? So please know the difference between hydrogen chloride and hydrochloric acid. Hydrogen chloride is in the gaseous state, right? It exists as a gas. Hydrochloric acid is in an aqueous solution, right? And you can get from hydrogen chloride to hydrochloric acid by adding the hydrogen chloride to water to form the hydrochloric acid. And that's basically how that is done. Here's another example, H2S, gas. The name of this compound is hydrogen sulfide, all right? Excuse me, when you add it to water, it now becomes H2S aqueous, and that is known as hydrosulfuric acid. And that's how you name that compound, all right? So that's basically how we name binary, let me write this up top here, binary acids. Acids consisting of hydrogen and one other element. That's how we name them. They all start off with the prefix hydro, then the stem of the name of the other element, then ic acid. Hydro, stem of the name of the other element, then ic acid. So that's how you name binary acids. So let me clear this here. So my question to you is this. What's the name of this compound? HBr gas. What's the name of this? Anybody?
Hydrogen bromide.
Exactly. Hydrogen bromide. Hydrogen bromide. Very good. So when we add water to this, or add it to water, it becomes HBr aqueous. So what's the name of this acid? Anybody?
Hydrobromic.
Exactly. Hydrobromic acid. All right. So that's basically how we name binary acids. Okay. But we have also some other types of acids which are known as oxoacids. And those acids, as the name suggests, will contain oxygen as a part of its formula. So as you can see in, for example, this case here, HClO, this is known as hypochlorous acid, HClO2, that is known as chlorous acid, and so on and so forth, right? So you might be wondering, how are these names derived? Well, it turns out that these names are derived from the anion from which they're formed, right? Let me explain what we mean by that. Let me go back to my writing pad here, and let me do this. So I'm going to use H2SO4 as an example, right? So let's say you did not know what the name of this acid is, right? But you do know that this is formed from the sulfate ion, all right? So this is a formula for the sulfate ion, and you can look up the name of this anion. When you look it up, you're going to see that it's sulfate, all right? So how do we name this acid based on this? Well, according to IUPAC, the name of the acid that derives from the anion is obtained by dropping the ATE ending and replacing that ending with ic acid. Oops, ic acid. All right. So for example, in this case, this is a sulfate ion right here. Then the name of this acid is the sulfuric acid. Sulfuric acid. All right. So basically, you drop the ATE ending and add the ic acid ending to get the name of the corresponding acid from the corresponding anion with the ATE ending. All right. So sulfate becomes sulfuric. Nitrate, let me do nitrate here as another example. To get from nitrate to nitric, we add a hydrogen ion to get HNO3 for each negative charge that is present. So this becomes nitric acid. All right. We drop the ATE ending and we replace it with ic acid. All right. Let me just say up here, I forgot to mention that up here, because you have two negative charges, you add two hydrogen ions to get the formula for the corresponding acid. All right. So for every negative charge, you add a hydrogen ion. For every negative charge, you add a hydrogen ion to the sulfate ion or to the 8 ion to form the corresponding acid. All right. Okay. Now there are other acids which have a different type of name where it's not ic ending, but ite, or I should say OUS ending. All right. So let me clear this. So let's take SO3 2 minus, right? This is called the sulfite ion. If you add H plus, 2H plus to this, you're going to get H2SO3, all right? And the corresponding name of this acid is sulfurous acid. So you see how we modify the name. The ITE ending of the corresponding anion is replaced by OUS acid, all right? So sulfite becomes sulfurous acid, all right? Here's another example, NO2 minus. This is called the nitrite ion. In this case, we would add one hydrogen ion because there's only one negative charge here to form HNO2. So this is called nitrous acid. All right. Again, the ITE ending is replaced by OUS acid ending. All right. So that's basically how we name oxo acids, acids which contains oxygen. All right. And if you go back to the table that I showed you earlier, you'll see that the rules I talked about apply in all these cases here. So this is known as a hypochlorous acid because that is formed from the hypochlorite ion, ClO minus. This is known as chlorous acid. This is known as chloric acid, and so on and so forth. So that's basically how these acids are named, all right? So just to recap a bit, binary acids start with hydro and end with the ic. We saw that earlier, like hydrochloric, hydrosulfuric, and then the oxyacids, the ATE ending is replaced by ic. And what's not mentioned here is what I just mentioned. The ITE ending is replaced by OUS acid. All right. So that's basically how we name these acids. Okay, I'm going to stop here for today. The next topic, we'll be talking about naming bases. All right. So are there any questions you want to ask about this, what we have just discussed, or anything in general? Any questions?
When will assignments be uploaded to Canvas?
I'll let you know. In fact, I was waiting until I finish chapter 2, and then I'll start uploading assignments based on those topics in chapters 1 and 2.
Okay.
Mm-hmm. Any other questions? Any other questions? Okay, if there are no other questions, that's it. So I'll see you guys on Thursday. All right, so take care. Have a good day.